Hi everybody, welcome back to Multirate Signal Processing. Today about optimization of filter banks or optimization in general. So last time we saw how to construct low delay filter banks, and we saw that there we have this structure or product of polyphase matrices. So our final polyphase matrix of the analysis consists of a product of individual matrices of lower order, which each have coefficients. Well, except for D was just given as a delay matrix, but F and G and so on, they have coefficients which then result in certain filters. So given the structure, we already have perfect reconstruction, but we don't know if those filters are good in any way, meaning good or sufficient stop attenuation and not much passband attenuation. So this is our goal now. We already have perfect reconstruction, but we still need good filters. So an example could be a desired stop attenuation of about minus 60 dB and a passband attenuation of less than minus 3 dB. Right? So it's a general rule of thumb. So here's the problem to solve. The coefficients which determine the frequency responses are the coefficients in our cascade or product that we just saw, the coefficients in our matrices, which are this EJI and or GIJ or the H and the F matrix. Right? So here this is from the F matrix, and the E and the J, they come from the zero delay matrix or also the maximum delay matrix. So they result in the frequency response in a nonlinear way because they come from a product. Hence, the usual filter design approaches don't work here. Previous approaches, like the Remes exchange algorithm, right? There we have basically just a linear dependency of the frequency response from those coefficients. So those traditional filter design algorithms can also be seen as optimization algorithms for more or less linear problems, or quadratic if we take the mean squared error. Right, so quadratic is also relatively straightforward, but here we have higher order products. So we can read out the resulting analysis baseband prototype impulse responses HA of n, for instance, by computing the sparse folding matrix of this product. So we compute the FA of Z, the diamond matrix, which has the polyphase components in this diamond shape, as the product of FA times the delay matrix times our cascade of zero delay matrices times the cascade of maximum delay matrices. Right, so then as a result, we get a matrix of this shape, and we know the meaning that this shape, this FA of Z, has. So if we have a polynomial, then we know that the polynomial in this place is this polyphase component of our prototype, of our baseband prototype. It's the downsampled baseband prototype, downsampled by a factor of 2 capital N, given these phase shifts here, this 2n-1 or n-1, and with all those changing signs here in the for every second polyphase coefficient. So here we can see the definition. So if we have these polyphase components, we know they are defined like this, and inside we see this HA. So from all those polyphase coefficients, basically we have all the HA coefficients. So we just need to read them out and put them in the right order. So in this way we obtain HA of n, and hence its frequency response from our matrix coefficients. So here we put the matrix coefficients in one big vector, so a collection of all the unknowns that we have in this cascade. So when we have those unknowns, then using this cascade we obtain our baseband prototype and we can evaluate it. So we can do the same for the synthesis side, or we restrict the submatrices to have a determinant of -1, in which case the synthesis baseband impulse response is the same as for the analysis. So in that case we don't need a separate evaluation. So this is actually the convenient case. Then we just need to evaluate or optimize the analysis part, because we know the synthesis part is the same. Yeah, so another possibility to obtain the analysis baseband impulse response is to compute the full polyphase matrix PA of Z, including the cosine modulation part, meaning including the multiplication with a DCT4 transform matrix. Its first column contains the polyphase elements of the first subband filter in reverse order, as we saw. Right? If we just take this FA of Z and multiply it with the first column of our transform matrix, then we have the polyphase components of our first subband impulse response. So this can be used to read out its impulse response, H0 of n, and to obtain this HA of n, the baseband prototype, we simply divide H0 of n by the modulation function for the first subband for k equals 0. Right? Since we know we have a modulated filter bank, we can just divide by the modulation function to obtain HA of n. So these two approaches can be taken for our optimization approach or the implementation. So we have to decide how to implement it, for instance, in Python. So here's our approach. Since we now have this nonlinear dependency of our baseband impulse response from the matrix coefficients, we need to use more powerful optimization algorithms, which are made for just mostly convex error functions. So Remes exchange is not working anymore, so here we have to look for more powerful algorithms. So for this, we first define an error function or objective function, and then we use an optimization algorithm to minimize this error function. This error function can be the sum of the magnitudes or the squares of the differences between our obtained frequency response, so what we get from our coefficients, given our unknown variables at some point, at some choosing some point, and our desired frequency response. So we choose some coefficients, look what we get, and compare it to our desired frequency response to see how far off we are. To give the stopband attenuation and the passband ripples different weights, we can also assign weights to the different frequency regions for our error function, as we already saw in the general filter design. So basically, we are now doing the same as for our general filter design, just now that we apply it to our baseband prototype. So our starting point is a vector of all of our unknowns of our matrices. So here we have our x, which is a collection of all our coefficients, right? And we now define a function which computes the baseband impulse response out of these unknowns by multiplying our matrices to obtain our final folding matrix or polyphase matrix, and then read out the baseband impulse response, HA of n. So that's the next step. This then yields the baseband prototype for our coefficient set x, which we call hx of n. Right? So this is the resulting baseband prototype for our coefficient set x. This is now used to compute a weighted frequency response at k frequency points with weights wi for each frequency point. So here you can see it. Here we have now our baseband prototype or window function hx given our coefficients in x, and now we multiply with e to the j omega I times n times wi. So omega I are now our frequency points at which we evaluate our baseband prototype, and Wi are our weights. So basically this looks like the DFT, except that we also now have the weights, and basically we can freely choose the frequency sampling points here. But it's actually implemented using the DFT using Frexy, right? So we use Frexy to compute this HI. By default it computes 512 equally spaced frequency points and then multiplied with the weights, right? So for each frequency component we multiplied with this weight. So we choose as many frequency points as necessary to sufficiently cover our frequency response. Usually it should be several times the length of our filter to avoid sampling the frequency response accidentally near its zeros. So remember, for the sinc function, which comes from an ideal low-pass filter, you have regular zero crossings, and we all want to avoid sampling the frequency response at those zero crossings. Or rather, this sinc function would result from a rectangular window function, right? So that's why we need enough sampling points in frequency, and usually choosing the number of frequency sampling points as several times the length of our filter is a good choice. The more important frequency points in terms of attenuation get the higher widths. So in this case, this would be the higher frequencies in the stop band. The same can also be done for the synthesis, but remember that this is only necessary if we don't have the determinant of our polyphase matrix unequal -1, because for that we obtain identical prototype impulse responses for analysis and synthesis, and we only need to optimize the analysis, as you can see here in lecture 13 and 14. Right, and that's why usually we take this approach. It makes things easier, and there are not many cases where you actually need different synthesis and analysis filters. So we also need to have a vector containing the weighted desired frequency response, which would be a factor 1 for the passband, multiplied by the corresponding weights, and zeros in the stop band. We call this D for desired. Our error function for a vector of unknowns x is now this. So here we have our obtained frequency response given our unknowns in x, and here the sum goes over the frequency domain sampling points. So here we take the difference between the obtained frequency response and the desired frequency response, di, at each frequency sampling point I. And we can also write this in vector notation. We have two vectors, one vector h, the obtained frequency response, and the vector d of the desired frequency response. We take the difference between those two vectors and multiply it with a conjugate transposed to obtain this function value, which is our error function or objective function. So here the first vector is a row vector, the second vector is a column vector, so out comes a number, a positive number. Yeah, so row times column vector. So now we just need to minimize this function f of x with respect to our vector of unknowns x. Right? Minimization here means we have the closest distance to our desired vector. This leads us to optimization in general. The goal of optimization is to find the vector x, which minimizes this error function f of x, and in optimization literature this is usually called objective function. We know in a minimum the function's derivative is 0. So if this f of 0 has a minimum, then the derivative with respect to x must be 0. Otherwise we could go down further. Right? So this is a requirement. This is necessary to obtain a minimum. An approach to iteratively find the 0 of a function is Newton's method. Take some function f of x, where x is not a vector but just a number. Then we can find its zero as depicted in the following picture. So here, this is now just a one-dimensional optimization. So vertically we have f of x, horizontally we have some x, and here in blue you can see the function. So in our case this f of x would be our derivative already, and we want to find the zero of this derivative. So then we start at some random starting point, x0, evaluate this function f of x, and we get some function value. And for this function value we compute the derivative, the first derivative, the tangent. Right? And then we follow this tangent and see where it hits the x-axis. So basically what we do here, we approximate this function by a linear function and see where this linear function becomes zero. So this is then our next guess, x1. So our x1, given that f of x would be linear, then we would be done. Of course it's not linear, so we have to re-evaluate f again, get a new function value, get a new first derivative, approximate this function again by this linear function, and get a new guess for the zero crossing x2, and so on. And you can see it quickly approximates the true zero. So here, this is the iteration. We start at some point xk, right? And then we update it by subtracting f minus the derivative of x at point xk. So this is basically going from here to here. So we go from xk to xk plus 1. This is our next point. And we can easily do this iteration several times until x doesn't change much anymore. So observe, sometimes we need to compute the derivative numerically by evaluating the function a few times in the neighborhood and, for instance, compute delta f divided by delta x for a small delta x. There are actually more involved methods which do it more precisely using more function evaluations. But the simplest one is this, where you just take two function values, f in the vicinity, so then you have a delta f, and you divide it by the corresponding delta x, and you get an approximation for the derivative. And this is actually also what we need in our case, because we usually don't have a closed form solution for the derivatives. So now we want to find the zero not of f, but of our derivative f prime of x, because we want to find the minimum, the zero of this first derivative, and hence we simply replace f by f prime, the first derivative, and we obtain this following iteration. So it looks almost the same, just that we start here with the first derivative and then we need to divide by the second derivative, the derivative of the derivative. Right, so this finds us then the minimum. And actually, to obtain a minimum and not a maximum, we need to have the condition that the second derivative is larger than zero. Right? If it's smaller than zero, then it's actually a maximum. Right? And that can happen too with this iteration. So here's a simple example. So it turns out that optimization is actually very convenient also for numerical mathematics, for finding solutions for expressions like square root of 2. Right? How do you find the solution of square root of 2 if you, say, don't have a calculator which has this capability? Or maybe how do you design such a calculator that it computes square roots? Right? Somehow the computation needs to be done in the machine. And this is actually an approach which is also quite common in numerical mathematics to compute roots, square roots. So internally they actually use this iteration. So we start with the function f of x equals x squared minus 2. Right? So x would be your solution, square root of 2. And then we see if we take the solution, square it, then we get 2, and we subtract 2 from it, and then we get 0. Right? So actually the 0 point of this function is the desired solution. So we can put actually any number here. Instead of 2, we can have a 3 or I don't know, a 10 or whatever, and then we have the square root of this number. Right, so very convenient. So this is actually then a formulation for a general square root. So now we can apply Newton's method to find this solution numerically. First we compute the derivative. Here we have a closed form solution. Right, square root of x is square root of this function here, which we want to find the 0 for, is simply 2x. So you can see also this concrete number doesn't really matter because it disappears in the first derivative. So all what's left is the first derivative of x squared, which is 2x. Right. So now we can actually formulate Newton's iterations. So this is f of x, or f of xk, divided by f prime of xk. And that's x squared k minus 2 divided by 2xk. So now we have our iteration, xk minus xk squared minus 2 divided by 2xk. And we can easily implement it, for instance, in IPython, as I did here. And because it's so easy, I can also do it here in my terminal window. So let me start IPython 3 minus pylab. Let's see if that works. No, somehow it doesn't work. So let's go to simply IPython. That works. So we take some starting point. This is x naught equals 1.0. So this is for k equals 0 basically. And then this is the update, right? So here you can see there is no k, because implicitly on the right hand side this is the old k, and on the left hand side we have k plus 1, right? This is the new xk. On the right hand side we have the old x, and on the left hand side we have the updated x. And in this way we don't need to actually use the index k explicitly. We can, but we don't need to. So here I copy it into my terminal window. So this gives us now the next xk. So let's see. Indeed, we get a new x, which is now 1.5, right? And now we can simply do it again. So we take this x and compute the next x. So this would be the x2 now. So here we have x 1.41. So this is already quite close to the true square root. So let's do it again. This would be x3. So now this one. And that's already quite close, right? So here compare it with the true value, 1.41, 42, 13, and so on. And here we have 41, 42, 1, and here it starts to deviate. So we already have 5 digits after the decimal point. So including the first one, we have 6 digits at accuracy. So that's pretty good after only 3 iterations. And because this this converges so quickly, that's why it is often chosen for software implementation to compute square roots. Right. So I actually can go on and have another iteration here. Let's see what we get then. So here fairly quickly converges. So now we have 3, 5, 6, 2, 3, 7, 3. Oh, this is pretty good. So up to this 7, right? So with this next iteration, we gained a few more digits. Let me do it again. And now basically we have full accuracy for all the digits that we display here. So that's pretty good. So total 5 iterations gave us the full accuracy So that's really fast. So it works, so we're happy. So here's an example for finding the minimum. Now the minimum of cosine of x. We know a minimum is at x equals pi, right? Cosine of 0 is 1, and cosine of pi over 2 is 0, and cosine of pi is minus 1, and that's the minimum of this cosine function. So this is also a way to numerically determine pi, right? So again, pi needs to be computed in software, for instance, or in some calculators, and this would be a way to do it. So here again, we first compute the derivative. So this would be actually then our function value to minimize, and that's why we also need the second derivative. So here the first derivative of the cosine is minus sine, and since we want to have the minimum, we also need the second derivative, which is minus cosine. Right? So again, easy enough. And this is then our iteration now for finding the minimum. Here we have first derivative divided by second derivative is sine divided by cosine. The two negative signs cancel, so we still have the minus sign here in the beginning. And that's it. Right? So this is our expression that we need to repeatedly evaluate, and here we can start at x equals 3, right? Just some convenient starting point. That's our guess for pi, right? So then this is our iteration. Again, on the right hand side we have the old x, and on the left hand side we have the new x. So here's our x. So here we can see, wow, it's already pretty good, right? 3.14, already 3 digits. Then let's do it again. So this is our x2. Here we already have 3.14, 15, 926, 533. So up to here it's correct, and here it's not correct anymore, right? So that's already pretty good. So after only 2 iterations, we get an accuracy of 10 digits. All right, let me do it again. And this is our x3. Here we have 3.1415, 926, 535, 897, 93. The last one is not exact, but that's pretty amazing again, that we have almost full accuracy after only 3 iterations. Yeah. Observe, here we can actually also start with x equals 1, and it converges to 0, which is a maximum. Right? So here you can also see that it can go in the wrong direction. So if we have a wrong starting point, x equals 1, let me try. Yeah, so here it goes into the wrong direction. And you can check that by evaluating the second derivative. So here the second derivative, remember, was the minus cosine. Cosine of 0 is 1, so minus cosine is minus 1. So does that fit? Yeah, so minimum, for minimum we need the second derivative larger than 0. For a maximum it becomes smaller than 0, and this is what we found here. If x equals 0, then the second derivative is minus 1, so that means we found a maximum. Right. Yeah, so this shows that we still need to check the second derivative to see if it is a maximum or a minimum. If we start with a totally different number, like x equals 100, it converges to 30 times pi, 32 times pi, which is a minimum, but perhaps not the expected minimum. So this also shows that the starting point is important. So our optimization finds some extremum. It can be a maximum or minimum, and it's not choosy. It takes any minimum which is nearby, right? So if you start at 100, you get a large number, which is still a minimum, but maybe not the one that we want. So that's something you need to keep in mind for optimization in general. It can get stuck in a local minimum, which is maybe not the one you want, and it can even go to a maximum. Yeah, so for our case, we have many unknowns, x, so we have a multidimensional function where the argument x is a vector, right? So the first derivative is a vector called gradient with symbol nabla. So this is the symbol for the gradient, because we need the derivative with respect to each element of the argument vector x. So this is the gradient, and this gradient consists of the derivatives of x to each of its argument components, right? Respect to x1 up to xn. So n is the number of unknowns here in the argument vector x. So should be argument. So the second derivative now is a little bit more complicated, because now we need to take each element of the gradient vector and again take the derivative to each element of the argument vector. And hence we obtain a matrix, the so-called Hesse matrix, as a matrix of second derivatives. So this is the Hesse matrix of f, and here we can see it consists of all possible second derivatives. So on the diagonal of the Hesse matrix we have the second derivative with the same argument component, right? x1, x1, xn, xn. So observe that this Hesse matrix is symmetric for reasonable function which we consider here like continuous functions. So here the derivative with respect to x1 and xn is the same as this derivative to xn and then x1. It's the same, and that's why it's symmetric. Yeah. Using these definitions, we can now generalize our Newton algorithm to the multidimensional case. The one-dimensional iteration, this one that we just saw, turns into the multidimensional iteration, where we now, instead of having a division by the second derivative, here we have this fraction because it doesn't sound if it comes from the left-hand side or the right-hand side. But for matrices, remember, matrix multiplication was not commutative. It means it matters if you multiply from the left or from the right. So here you can see if the gradient vector is a column vector, then the matrix inverse has to come from the left-hand side. Otherwise, we cannot multiply the two, otherwise it wouldn't fit. But apart from that, this Newton update works. So we have the new vector is the old vector minus the inverse of the Hesse matrix times the gradient of f at point xk. And for a minimum, this Hesse matrix now must be positive definite, which means all eigenvalues are positive. So this corresponds to the second derivative being larger than 0 in our one-dimensional case. So here it is the eigenvalues of the Hesse matrix which must be positive. So if n is large, then we have a problem here, because for the Hesse matrix we need to compute n square second derivative, which can become computational complex, and then we need to also invert this matrix. So remember, we have second derivatives in h, and so for the second derivative, for each of those second derivatives we need at least 3 function evaluations to compute it, and that we have n square of those. So if n is large, say if we have a high number of subbands and many of those matrices, then this becomes prohibitive, especially if we need many iterations to come to a good solution. Yeah, so hence we now make the simplifying assumption that the Hesse matrix can be written as a diagonal matrix with constant values on the diagonal. So observe that this is mostly a very crude approximation, but since we have an iteration with many small updates, it can still work. So this is actually quite a dramatic simplification. Instead of taking all those second derivatives, we say we ignore those mixed second derivatives. We assume they are very small, and then we also assume that all the second derivatives with the same variable are identical and have a given value 1 over alpha, right? So that's also a quite restrictive assumption. So here the best value of alpha depends on how good it approximates the Hesse matrix, right? We don't even know this value here, right? We just assume it's all the same on the diagonal matrix. So it's quite a harsh approximation assumption, but since we do this approximation many times, this iteration many times, we hope that it still works, as long as this somewhat fits. Yeah, so we still don't know the alpha, but let's see what we get. So our iteration with the inverse Hesse matrix now turns into simply this update. So instead of computing this inverse Hesse matrix and multiply it with a gradient, we now have this factor, this float value alpha, and multiply it with this gradient vector. So this is a lot more simple, right? So we simply ignore this Hesse matrix basically and replace it by this float value. Yeah, so this is much simpler to compute. This is also called the steepest descent because the gradient tells us direction of steepest descent, or gradient descent because this goes in the direction of the gradient. And because it's so simple, it's quite widely used. And often it actually works quite fine. If this assumption of our Hesse matrix is true, at least to some degree. Yeah, so we see that the update of x consists only of the gradient nabla f of xk scaled by this factor alpha. In each step, we reduce the value of f of x by moving x in the direction of the gradient. If we make alpha larger, we obtain larger update steps and hence quicker convergence to the minimum, but it may oscillate around the minimum because we may overshoot the minimum. For smaller alpha, the steps become smaller, but it will converge more precisely to the minimum because there's less overshooting. Because of the update direction along the gradient, this method is also called the gradient descent. So here's a simple example to show how it works. I made up this simple two-dimensional function, x1 and x2, now two unknowns. So very small gradient consisting of cosine of x1 minus sine of x2. Right? And we want to find the minimum. And we know the minimum of cosine is again at x1 equals pi, and the minimum of sine is at x2 equals 1.5 pi. Right. So this is the gradient. Minus sine is the first derivative of the cosine, and minus sine derivative is the minus cosine. So here we have the derivative with respect to x1. Here's the derivative with respect to x2. Yeah, and in IPython we choose alpha equals 1 as a starting point. And also x1, x2 equals 2, 2. So alpha equals 1 is fixed. We actually don't change it, but here's the starting point for the x. So here alpha equals 1. So this would be actually a factor in practice you would try out which works best. So this is just some guess which we take and see if it converges. And often what you do if you find it's not really converging either fast enough or it's oscillating, then you change alpha. So if it's oscillating, you would reduce alpha. If it's too slow, you would increase alpha and start again. Yeah, so here's the starting point. Copy, paste. Here's our x. So now you can see the x consists of those two values, our array. And this is now our update formula. You can see the new x, the new array x is the old array x minus this alpha times our gradient. And here you can now see the gradient. Here's the x1 and here's the x2. So here's our gradient descent. You can see it's really simple. We just need to have those two derivatives. Not even a second derivative is involved here. Remember, the second derivative is basically absorbed in this alpha, and that's why we don't need to compute it, and that makes it so easy here. So this is our update now. So let's see what we get. So this is our x1. Here you can see it. And next update, this is x2. Next update, here's x3. It's actually quite good. So here you can see pi is the minimum of minus sign, right? So that fits. And here we have pi over 2, and actually, yeah, this is the function. So pi is the minimum of the cosine here, right? And minus sine x2, here we can see pi over 2. We have the minimum of minus sine of x2. Yeah, so this is what we have here. So we see the minimum is obtained for x1 equals pi. Here's the exact value, and x2 is pi over 2. Here's the exact value. And you can see it actually, again, was converging quite quickly. So you can see here 3, 3. So it actually has full accuracy in this case here. And here 3, 9, 2, 6, 5. Yeah, again, the digits that are displayed here are correct after just a few iterations. So that's quite nice. So observe that we needed just 3 iterations to obtain 9-digit accuracy in this 2-dimensional case. In the 1-dimensional case with the Newton iteration, we only needed 2 iterations for the same accuracy. Right. So even though we didn't compute the second derivative, we already get quite a nice solution, actually for 2 numbers, for pi and for pi over 2. So that's quite nice. Yeah, so here's a Python example for the optimization of an Mdct filter bank. Here we now construct our error function or objective function. Right, so the optimfunc mdct.py contains an optimization of the baseband prototype with determinant equals -1. So here the determinant of the polyphase matrices for a given number of subbands, and set in the main part of the program. For instance, here the number of subbands n equals 8. And we can execute it in the terminal shell using Python and then the function name. So let's see what's inside. So let me quit this and open gedit optimfunc mdct. And here you can see it. So here's now our error function or objective function for the optimization. X contains the unknowns from our matrix coefficients, and capital N is the number of subbands. So here you can see I'm importing the matrix types here, and also the matrix multiplication function polmult. Here the delay matrix. Here the symmetric F matrix, which has the determinant equals -1. And here this conversion from the FA of Z matrix to the baseband prototype H. Yeah, and here I compute now the polyphase matrix. Here first FA, then here the delay matrix. Here I'm multiplying the FA matrix with the delay matrix, and then I'm extracting the H matrix. So this is actually an Mdct type matrix where we just have the FA. So the coefficients in X, they are then 1.5 coefficients, 1.5 n coefficients, and they make up this matrix FA because the last n half is given by this determinant equals -1 condition. And here we have the H, which is our prototype, right? And here I'm computing the frequency response. So here with Frexy with 1024 frequency sampling points. Here I'm defining my desired frequency response. Here's my passband, the desired passband. So when we have 1024 subbands or sampling points, not subbands, sampling points, divided by the number of subbands here and divided by 2 because this is the prototype, which is symmetric around 0. So the bandwidth of the prototype is not the total bandwidth divided by n, but half of it, because half is positive and half is negative. Yeah, so here I'm constructing then the desired frequency response as a sequence of ones in the passband. Then we have a sequence of zeros in the stop band. So here we can see the rest is all stop bands. Here I'm defining the transition band, which I'm defining basically as the same as the passband. And that's important for the weights, which I'm constructing now. Here are the weights. They consist of ones in the passband and then zeros in the transition bands, because I don't care what happens in the transition band. And then the factor of 1000 in the stop band. So I amplify the effect in the stop band by a factor of 1000. Yeah, and then finally I'm computing the difference between the obtained frequency response and the desired frequency response. I'm taking the magnitude and multiply element-wise with the weights and then sum it up. And that's our error function, the resulting error. Yeah, so this is our error or objective function, and then we can run it. So here you can see I'm using SciPy Optimize as an optimizer here. SciPy Optimize actually has several quite nice optimizers, which is convenient here in our case. Here I'm importing everything else necessary. Here I'm choosing a random starting point for n equals 8 subbands. So here I can actually change the number of subbands if desired. Here I'm taking some random starting point. Here's the starting error for this starting point, which is convenient to see how the error reduces from the optimization. Here I'm using the function optimize minimize, and you can see the first argument is the function name of my error or objective function. Here this x0 is the starting point, which also tells the minimize function the dimension of my unknowns. And here is additional arguments to be passed to my error or objective function. Here it's the number of subbands. Then here options, here I'm displaying the progress of optimization. And then I'm displaying the solution. This is the minimum found, the argument. And here I actually save it in a text file, so that it can be used in some other program, for instance. And this is the error obtained from this minimum. Yeah, and then we can actually evaluate it in terms of our baseband impulse response. Here I'm computing my polyphase matrices from this obtained minimum, so FA, FAZ with a delay matrix. Then I'm extracting our baseband prototype from it and plot it. So here you can see the resulting baseband prototype. And here I'm computing the frequency response, the magnitude frequency response using FracZ, and plot the dB number of the magnitude of it. Yeah, so that's it. So SciPy comes to the rescue, SciPy minimize, very convenient. So now I'm executed. Python, let me see if Python 3 works. So this is the starting error, quite high, large number. And that comes because of the high weights I have in the stop band. So now it's busy doing something and it's not displaying much. And I can actually tell from the fan going on that it's busy with something. And it takes a while. Takes a long time. Yeah, maybe Python 2 is faster. Let me try that one. So here again the starting error. Again, similar size, but it seems it's also not really faster. And that's also a property of optimization. It might take a long time depending on how complex the error function is, or the objective function, and what the dimensionality of the argument vector is. Right, if you have many coefficients and you have a complicated error or objective function, it needs to compute many steps and many gradients and derivatives, and that can take quite some time. And you can see actually here in this blue bar that it's busy computing things, and it's not quite done yet. Yeah, kind of interesting. It takes a long time. Oh yeah, now you got the result. So here you can see now the result. In figure 1 you can see the resulting baseband prototype, baseband impulse response of our optimized Mdct type filter bank. Right. So it almost looks like a sine window, but not quite. So it looks a little bit more flat here. And then you look at the resulting frequency response, and you can see here the passband, drag it down a little bit, is about at 20 dB. The absolute number doesn't really matter here, it's relative. And you can see here 20 to maybe -5, so we have about -25 dB attenuation. And then this part has somewhat higher attenuation than in the sine window, and it's more flat. In the sine window it was going down a little bit more, and here it's a little bit more flat, and this is because basically this first side lobe here is still part of, at least partially part of the transition band, and then here we have the stop band, and the stop band has the same weights everywhere. So that's why the ripple height now became more similar than in the non-optimized sine window case. So here we get about -20, so we have about -40 dB stop attenuation. Not great, but it's kind of okay. Yeah, so this in principle is how it works. So if you want to have more attenuation, for instance, you could choose the transition band wider, for instance. Yeah. So here it optimizes the coefficients using SciPy optimize minimize. It needs SciPy version 0.19.1 or later. And after finishing the optimization, prints out the resulting error value. Let's check the error value that we obtained. Here, error after, still quite a high value here. It's far from perfect, but much less than in the beginning. Yeah. So, and then plots the resulting baseband prototype and its magnitude frequency response. For n equals 4, it is fairly fast. Observe that n equals 8 subband already takes some time, as we just saw, right? And n equals 16 takes a lot longer, so I leave that up to you to try it for larger n's. So here's the resulting plot for n equals 4. So here we can see it. We have now 8 samples for the window. So this is the simpler version than the one that we just saw. Maybe you can also try it here using n equals 4. So save it. And now do the same thing. And we have a starting error. And it's again somewhat busy here. Takes a little. Maybe you can let it run in the background. And here's the resulting frequency response for n equals 4 bands. Yeah, now we have it. So it's indeed faster, but it's not blazingly fast. Right, so again, similar shape, but now for n equals 4. Yeah, so observe that the resulting baseband impulse response is similar to the sine window, but not exactly the same. It is more optimal in our optimization function sense, right? Yeah, so that should be it for this part. So this should be maybe a nice start for your own trials. Take this function and try different n, like n equals 8, n equals 16, and maybe also try different weights or different transition bandwidth, and see what you get from this optimization. Okay, so thanks for your attention and see you next time.